Yeah. Good afternoon, everybody. So first of all, I would like to thank organizers and our partners, Keysight Technologies, for bringing this opportunity to speak here. We have a little table down there at the back, so you can see some of our instruments. And if you have any questions, we're available here today and tomorrow. So please ask, and we are ready for discussions. So first of all, I would like to spend maybe 2 minutes explaining what is Keysight Technologies. So actually we started many years ago as Hewlett-Packard, and Hewlett-Packard was a company that actually started as a manufacturer of test and measurement equipment. So now we know this is more related to computers, but initially it was a test and measurement company. Then we been Agilent Technologies, and we had maybe optical guys here know about spectrophotometers and this kind of stuff that was manufactured by Agilent. And now we're focused only on electronic measurements and we're Keysight Technologies. And since I'm talking right after a superconducting paper, I tailored my slides to be in resonance with this paper. So this is typical pictures from the lab. Maybe Evgeny sees this every day and listen to these pumps working all day round, right? Yeah. So actually, this is a Qubit, IC Qubit chips, and this is a cryostat. And this is a room temperature electronics, which is used for performing different kind of measurements and experiments. So actually, we are the company that makes everything that is located inside this rack. So if we will look at different components of cryogenic system, of course we have solutions for non-cryogenic systems like optics and atoms and different kind of other implementation of qubits. So if you look at cryogenic system, we have solutions for any part of life cycle, starting from design software, where you can design your qubit or design some parts of your control system or your cryogenic electronic, some amplifiers, for example. We have conventional instruments like network analyzers for your qubits. You can also test your cryogenic systems. And we also offer, with our partners, some wafer testing, where you can, at temperatures of several kelvins, you can measure at wafers your chips or your amplifiers, for example. So what we are doing a lot last years, we are building qubit control systems. So this is a simplified diagram for most likely, I would say, solid-state qubits like superconducting or maybe spin qubits, and it consists of, as you can see, a number of signal generator, because as was explained in the previous lecture, you will need to generate pulse, microwave pulse to control your qubits and to read out the state of your qubit. And here you have different components from the hardware side and from the software side. So I will come back later to this, but first of all, I would like to speak a little bit about qubits and why, and what is required often from a guy who is making experiments to what is required from him to control this system. So what is a qubit and what is different from classical bit? So the quantum qubit, it exists in a superposition of 0 and 1, or a ground state and excited state. And often this state is shown as what is called a block sphere. So actually it's a vector, and you can describe the state of your qubit as a vector on this block sphere. And if you want to perform any operations, if you would like to build a gate-based computer, you need to have somehow to control the position of this vector, and as it was perfectly explained, you will need to have control pulses. This is called a pi pulse because this pulse rotates a vector by pi or 180 degrees, and this is basically a NOT gate, so it transfers your state from 0 to 1 or back from 1 to 0. So in order to make this pulse, you need to do actually a lot of experiments. You need to calibrate your amplitude and the duration of this pulse to make sure that it rotates your vector exactly at 180 degrees. So this is a problem that is, I would say that maybe one of the first problems that is solved by experimental physicists in qubit area. The same for readout. When you read out your qubit, it collapses to one of states, so all the superposition is killed. So you have to do many repetitions of the same experiments to get statistics and to see what was the superposition state where your qubit existed. So you need also to make a number of measurements. So if we will look at gate-based quantum computer, and this is one of algorithms, for us, for engineers who design qubit control systems, this is basically a sequence of pulses. It could be radio frequency pulse, or it could be some voltages, maybe low frequency pulse, and we need to program them really precisely. And here you see some problems, maybe some points to note. So this could be some high frequency signals. You will need to control amplitude and phase because you use IQ modulation. You often use a frequency division multiplexing if you have many qubits in your system, and so on, so on. So basically, at the end of the day, we see that many science groups, they really need to combine a deep knowledge of physics and a very good understanding of control electronics and very good knowledge of how to program these control electronics to create right sequences of pulses. So it's not an easy task. Usually there is only one or maybe two person in the lab who knows a very good programming and radio physics and the, let's say, superconducting physics. So it's not too easy to find this kind of person. So here's a list of typical experiments that usually are made with qubits. It's Rabi oscillations. We've seen this graph today in the lections, and some other experiments, and all of them made to measure I would simplify this a little bit. So they made to measure a lifetime of qubit, because the superconducting qubits, the lifetime is really short. You want to see, if you're a manufacturer, you want to see how your manufacturing process affects your lifetime, for example. If you're building some algorithm, you're also interested to do as much as possible operation during the lifetime of qubit. So what we decided, so now I'm going to speak about a little project we have inside our quantum solution team, which is mostly based in States and in California. So we decided to make a qubit emulator, because you guys, well, at least some of you who work with qubits, you have a real qubit in your lab, and you can have experiments, you can debug software, debug your control algorithm with a real qubit. We don't have this. So we decided to make a qubit emulator which will behave something like superconducting qubit. So we have a digitizer which captures, so I will skip this down conversion part, it's not important right now. It captures control signals coming to qubit, and at any time of we know the state of our qubit, and we see how control signal as a control input will change the position of this vector. And depending on this current state of qubit, this algorithm reacts differently on readout signal. I will show this more in details. So, first of all, we made an FPGA image, so it works in real time. So we control the state of qubit, and any 20 nanoseconds we update the state of the qubit. We have some, I would say, probabistical engine that make qubit collapse to 0 or 1 as a reaction to readout signal. The user can set T1 of qubit, and this defines the probability of relaxation. And of course, the user sets the resonance frequency of the qubit and the coupling strengths between the qubit and the readout to the control line. And of course, T1 is explained. So for readout, now it is not frequency dependent, so we decided to not make it so far. As we are using FPGA, we are not doing it really fast, but it is still about 500 nanoseconds. So this is not bad. Usually the signal propagation through the cryostat takes several hundreds of nanoseconds, so it's not as bad. And here you see the readout result. So actually, what we are doing, let's look at this diagram. So we see by the amplitude in what state our qubit was. So we see the different amplitude of readout signal depending on 0 or 1 state. So I will show you some results explaining how it works. For example, if our qubit was in ground state and we put a readout signal, the output signal will have the amplitude as defined by user. The 0 state's amplitude is 0.5 and 1 state amplitude is 1.0. So if we will have some control signal that will at pi pulse that will put our qubit in a 1 state, an excited state, so this qubit simulator will give us the amplitude of 1 at the output. So this happens in real time. So we are putting a control signal, we are putting a readout signal, and that gives us the amplitude. So, for example, if we will apply pi pulse 2 times, for example, and we'll put it back to the ground state, we will see the amplitude corresponding to ground state. If we'll apply a pulse that rotates vector on 90 degrees, so in this position, the emulator will work on randomly. He'll randomly provides different amplitudes corresponding to 1 or to 0. So it will give you some very similar result as happens in real time. So we can do some basic experiments, by the way. So Rabi measurements. This experiment is made to define a T1 time or pi pulse time. So you put control pulse of different lengths, and then you measure what was the position of the state of your qubit. So this is basically the result. Of course, each point is a large number of repetition of the same experiment. So you really see, with the emulator, you can really see this kind of oscillations. And you can even detune a little bit from the resonant frequency. And you will see some kind of decay of your amplitude. And if you will put decovariance, if your emulator, if you will turn it on, you will see behavior like this. So here you can see the really, well, if it could be really. So the results obtained from the emulator using the scripts that we are providing. So basically we are providing to our customers example of control scripts for making all these kind of measurements. like Ramsey, measuring like spin echo and randomized benchmarking, so many kinds of experiments. So if you will run them on an emulator, you will get the results that are really similar to what you have in the real life. So it could help some students, it could help some guys who don't have access to real Qubit. You can really play with different parameters of your control software. You can test if your control system works exactly as you expect it to be working. Because in the real life Qubit, you have so many things that can go wrong, and they will do. You may have issues with cryostat, you may have issues with amplifiers, bad contact somewhere. So you will spend weeks just pumping your cryostat back and up and down and cooling it down and heating it up. So you will spend weeks just to debug your hardware. And here you can play with the control algorithms very easily. So as you can see, it gives some kind of noisy results. So we try to make it really lifetime, like in real life. So the last thing I want to say that this is not a product we are selling right now. So this is more a research that we are doing for some internal debugging of the control scripts that we are providing. So basically, again, I want to, if you have any questions during today or tomorrow, we are open for discussion. So please ask questions if you have any. Okay. Thank you. Well, I would say that hardware, I mean the hardware part which runs the FPGA, it's about 20K. So it's maybe you can buy cheaper as a components, of course, but it's an instrument, so it's more expensive. But the FPGA image algorithm, so far we're not selling. We're working on enhancing some features.
So you said it's not yet a product, right?
Right.
So when do you think you can deliver it, and what will the product look like?
I don't know. Well, I think that's. I hope we will get some version for customers, maybe closer to the end of the year. But we have some beta code now, so we are playing with it internally in Keysight. So if you're interested in demo, we can do this.
How does it compare to this one?
Well, that's a good question actually. So what I was talking at the last part of my presentation, so this is a solution to test control systems like we are doing or other companies doing. So if we will come back to the Qubit control systems that we are doing. So first of all, we are faster. So if you take a feedback loop, which is important if you want to do decision making, or if you want to do active reset of your Qubit, you need a feedback loop, so we are faster. And we are more scalable, so we have some big customers, I would say, and we have much more channels that we ever seen with these guys. So we have a modular architecture, so we can add as many channels as we want. So this is most important. So we have very fast feedback loop, and we have more channels.
I just wonder, can you couple it with real qubits and then use it as a part of some sort of machine learning algorithms, quantum relational algorithms?
Yeah, that's a really good question. So actually, we are not doing this machine learning algorithm yet. So, but we are using these signals from real systems. So, with some customers, we work together on enhancing our algorithms. So, when we are using real system for debug our algorithms and our control software. But we are not using machine learning yet, so that could be a really good idea, by the way.
Well, any other questions? If not, let's thank the speaker again.